Good afternoon, my name is Peter Duenas.
And I'm Keaton Dybdahl.
And today we're doing our CIVL 302 project with Dr. Colleen Bronner.
In this video, we're going to be discussing curve fitting and how it is used in engineering applications.
Stay tuned. So to continue with our topic of curve fitting, we might as well talk about how we as engineers use it. We work with data a lot. We like to observe trends, like to use those as tools. Maybe it's when we're calibrating equipment or when we're making economic decisions, we like to be able to make educated decisions. So some common examples of this we'd see in engineering, maybe money versus time. Maybe we're recording our revenues and stuff. Hopefully they're looking something like an exponential growth type of thing, but this is just, this is a model that we are fitting to our set of data to, show what we're doing with our money over time. Another one that we use, and we'll be talking about later in this lab, is for flow rate. So in our fluids lab this semester, we talk a lot about different types of flow rate. There's different ways of taking measurements, and one of the ways we do that is with a weir, and with that we plot our flow rate as a function of the height of the water on the weir, and we have pictures that you can observe this from. But basically, we come up with a, we have our data or whatever, we're observing our flow rates and stuff, and we come up with a line or a curve that goes through there, and then that helps us make decisions. Maybe it's when we're calibrating pumps or just different situations. And we'll talk a little bit more about that later in the lab, but remember the tools we use for interpreting our data and making assumptions about our interpolation, and regression. These are both tools we use to curve fit to our data. So interpolation can basically be explained by estimating a value in between two known data points. So for example, if we had our data all spread out, and we wanted to come up here and know what our value is in between, x1 here and x2. Well, we could take a curve that comes up here and goes through x2. Maybe we want to know, does it go through x3? How does it fit the rest of the data? So interpolating is basically going between each data point and fitting all the data points into your basically curve.
As Peter was talking about, interpolation is a part of curve fitting, and so let's say, for instance, you're given a table, say in your thermodynamics book, and you want to know a value that really isn't in the table, but it falls between two certain values. And let's say this table looks something like this. We have a temperature against pressure. Our temperatures in degrees Celsius, and our pressures in kPa. Say we have 205 degrees Celsius for our lower end, 210 for our upper bound, and 1724.3 for the lower end in pressure, and 1907.7 for our upper bound in pressure. So, using interpolation, the equation for interpolation is given by here, where capital P is our desired pressure, this is our temperature given. Alright, so let's say, for instance, we want to find the pressure at 209 degrees Celsius. So our pressure at 209 degrees Celsius equals 1. So that pressure would be our desired pressure. And in this case, we have T1. This would be our T1. This is our T2. This is our P1. This is our P2. Alright, and using the equation given for interpolation, we can see that our pressure equals, we have our P1, which is 1724.3, plus our temperature that we want to find, which was our given temperature, minus our T1, 205 degrees Celsius, over our delta T, which is 210 minus 205, and then we have 1907.7 minus 1724.3. Alright, when you crunch that out, you get a pressure of, it came out to 1871.02 kilopascals. And that's an example of a linear interpolation when the table does not give you the value in between. And just make sure that the table is in fact a linear relationship between pressure and temperature.
Regression, on the other hand, works a little bit differently. That is where we actually build a model function to basically tell us how different, how far off the set of data we are. So let me draw that. It might be easier to explain. So regression might, not go through every single data point. Got y and x here, but it might do a best fit line going right through the center, or maybe the best fit line happened to be a polynomial of some kind. Who knows? That's just it could be on any order, but regression is fitting a curve, and it's the way that works is it's taking all these little differences here between our model function that we come up with. We'll call that y bar. And if it were a linear model, which linear regression is probably one of the most popular types we do in engineering, it would just have a linear form, mx plus b, and these would be coefficients that are come up with through your curve fitting process.
Alright, so I'm going to talk a little bit about what a residual is and how it plays into your model here. We have a set of data here. It's actually, we're going to call this age on the x-axis versus height. And we're going to want to come up with a best fit line that represents our data set. And in doing so, you could use, software. You can do it by hand, which what we're going to do here, just get a visual representation of what's going on. But you can use software such as like Excel or R to come up with your best fit line, which is a lot more accurate. And so let's just plot that line. You're going to want to make sure it best represents your data set. Let's say right there. Alright, and as you can see, that line takes the form of x plus b. Alright, and as you can see, our model is not perfect because all of our points don't lie on that line. And that's also because of error, uncertainty in our data, which happens in the lab, taking measurements. You're not always going to be right on. And so what a residual is actually the vertical distance between your predicted y versus your model, which would be this distance right here. And say, for instance, this would be a positive residual, this right here, this segment, because it falls above the predicted y, or our mean y, or model y. And let's say this one right here is a negative residual, it falls below. And right here it actually came out really nicely. See, that point falls exactly on the line. So that would have a residual of 0.
So to kind of tell us a little bit about how good a regression model or an interpolation fits our data, there is a statistic that we use called R squared, the coefficient of determination, and I'll talk about that here in a second. So now that we've talked a little bit about curve fitting and what residuals are, I want to talk a little bit about how we know which curve is the best to use or which curve best fits our model. So we'll do another example here. X and Y. We got our data set. Now, there are lots of tools that we can show the measure of goodness of fit for our curve. Probably the most popular that we use that's incorporated into a lot of software is called R-squared. It's the coefficient of determination. And what that is, like I said, basically a measure of goodness of fit of your curve. So let's say that our model function came up here and, you know, maybe the model function that the software came up with was just a straight linear fit. Now obviously we could see that's not necessarily the best fit for the data. We have like some pretty big residuals over here. But what R-squared does is it compares the value of your residual, which we can compute this formula. Where yi is your individual data point and y model or y hat is your model function. You can see that this subtraction gives you this residual, and we square it so that it's just the magnitude. We're not interested in whether or not it's above or below the model function. We just want the magnitude. So what R-squared says is it takes this residual function and it compares it to the average value of the data. So let's say that, kind of change directions here. Let's say that this line that I drew is y bar. That's the average value of the data. Say our model function, maybe it came up with something a little bit better. It incorporated a few more curves. So maybe it came up with something like that. You could see how the residuals would be less at points like this, maybe a little more here. But what we're going to do with R-squared is compare our model function with the average value. So let me get the rest of this equation. That's our difference between the data point and the average, so our residual to the average function. And we're going to compare that to the original average function. So we can see what R-squared is it's just the ratio of improvement that our model function is to our average function. And so that being said, you know, an R-squared value of 1 means that it's 100%, you know, a better fit than the average function. And whereas an R-squared of 0 is telling us that we might as well use the average function because it's giving us the same residuals as our model function, which means it's not much of an improvement. So our goal with R-squared is to try to see how good this curve matches our data set. Practical engineering example, we're going to talk a little bit about a fluids lab that we had this semester. So before you have a data table. This is our data that we collected. So basically we ran an experiment to measure the flow rate of a triangular 61-degree V-notch weir. And the way we measured flow was by using a weigh tank, capturing the weight and dividing it by the density times gravity times the change in time. That's just part of the experimental procedure. So what we ended up doing with this is coming over here and calculating flow rates in relation to height using this equation, which is a calibration for this particular weir. So to give you a little bit of an example, come down here. Here is our plot of our data. As you can see, we have flow over here on our y-axis and height on our x-axis. So to show you a little bit about how to curve fit, there's some software incorporated into Excel here you could just click on your data set, right click I should say, come down here to add trend line. It's going to bring up a table of a bunch of different shapes. We could have, you know, you could see an exponential fit, linear, goes right through everyone, logarithmic. So there's a bunch of different options you have when choosing the correct curve or your desired curve. You can see a polynomial fits pretty well there. I think we're going to go exponential here. You also have the options of displaying the equation of that model function, as well as the r squared, which we talked about is the goodness of fit of that function. What we wanted to do for this experiment was do a linear regression. As you can see here, this data isn't exactly linear. So there are several things we could do in this case. One of the strategies is to transform the data. If we come up here, we can see that H here looks like it has it's related, it's directly proportional to 5/2. Q is proportional to 5/2 H, excuse me. So we're going to transform our H so that it is in the 5/2 scale. So that's what we did down here. We took our flow rates versus our heights here. And as you can see, it looks a little bit more linear now. And we already went through and added this curve. You can see it's y equals mx plus b. These coefficients and intercept are actually performed as a part of the regression analysis in Excel. That's a whole separate tool that we'll show here in just one second.
Alright, so after you've come up with a linear representation of your model, maybe you want to run a regression analysis on your data set to kind of get a level of confidence in your model function. So in doing that, you can go to File, Options. Going to go to Add-ins, Analysis Toolpack. Going to go OK. And up here, under Data, you have Data Analysis. And you're going to want to go to Regression. Alright, Regression right there. And you're going to want to input your range. Say your Q, you have Q here, flow rate. And then in your X, you have your height to the 5/2 power, which was transformed. Alright, and since I included the labels, we'll click that one. And we're going to have a 95% confidence level here. Your confidence level can be chosen based off your individual choosing. So we're just going to go with 95%. We're not going to choose constant is 0 here, because that is not the case for our model. And we're going to click on residuals down here, and we'll even show you a residual plot, show you what that's all about. Alright, and we're going to go OK. And Excel spits out this for you, which is a residual plot right here. Alright, and so I'll talk about what this really is. So here you have your coefficients. That would be your, for your function, which would be y equals, so your intercept would be, so you have your slope right here. This is your slope, your h to the 5 tab, which is right there. So it would be y equals 0.0139978 x minus, in this case, because our intercept is negative, 0.00445 plus some sort of error, which is unknown in this case, really. And that's what you're going to get in real life scenarios. You're going to have error in your data. So that's the function that was came up with from regression analysis. And so I'll discuss a little bit more. We have our t-statistic, which is a measure of confidence, also used in statistical analysis properties. And also we have a p-value, also just a measure of confidence in our data. And so here we have a residual plot of our data set. As you can see, it's kind of showing a little bit of a trend here. It loops down near the middle section. That's hard to show you there. So near the lower flow rates, we're having positive residuals, and at the upper flow rates, we're having positive as well. And all in between, we have negative residuals. This could indicate some sort of bias.
You could also run more tests if you have more time to see if this is actually true for all your flow. All right, and lastly, I'll cover on r squared. This is our coefficient of determination. So we had a 0.987143 as our r squared, which is, this basically tells us that our model function with an r squared of 0.987 is a 98.7% better fit for the data than the average. And so for instance, in our case, we had a linear regression. You could make this r squared be as close to 0.99999, but that doesn't really help you out with your model.